Hi, thanks for tuning into Singularity Prosperity. In the previous video on this channel, we discussed the evolution of the field of computing, from as early as the Chinese abacus to the integrated circuit. To expand on that, this video is a culmination of a series of documentaries from the vacuum tube, transistor, and integrated circuit eras. The reason I wanted to do this is to provide further insight into how computers have evolved, highlighting the exponential growth from less than half a century ago, and providing further background context for future videos on this channel. Additionally, so we can appreciate the advances in modern technology we all often take for granted, and the humble beginnings they came from. Enjoy the documentaries, consider subscribing, and let me know your thoughts on the subject matter in the comments below.
Electronics is a science that applies these tubes to the service of man, to the speeding of production, to the winning of the war. To understand how electronic tubes work, let's take a good look at one of them, one that's representative of its species. This is a diode, a typical two-element electronic tube. Let's get inside it. In fundamental operation, it resembles an ordinary single-pole switch, a switch that can connect, for instance, this battery and its motor load. One power lead comes to the anode, the other lead goes to the cathode. When this switch is open, the contacts are insulated from each other by a vacuum, or by some inert gas inserted into an evacuated tube under low pressure. To close this switch electronically, all we need do is heat the cathode and give the anode a positive potential. Then here's what happens. As electrons are emitted from the surface of the heated cathode, being negatively charged, they fly at tremendous speed to the anode. In this way, a current-carrying path is formed, which closes our electronic switch and permits our motor to operate. You'll notice, by the way, that the direction of electron flow is contrary to the orthodox concept of current flow from plus to minus. Now, at this point, you may ask, if an electronic tube is basically just a form of switch, why is electronics hailed today as the technique of a new engineering era? To answer that question, let's review 6 of the basic things that we can do with this new kind of switch. In the first place, we can rectify current with it, converting AC to DC. We can do this merely by connecting an electronic tube in series with an AC circuit. As you study this circuit diagram, note that only each positive half wave of AC voltage will now produce a current. When the anode is negative, the electrons are repelled and no current flows. In other words, because only the cathode can emit electrons, we have here what amounts to a one-way street. We can visualize the result of the tube's rectifying action with the aid of these 2 oscilloscopes. The one on the left shows alternating current coming in. The one on the right shows pulsating direct current going out. The applications of this basic rectifying principle are many and important. Here's one of them, changing AC to DC on the nation's electrified transportation systems. Here's another, rectification for electroplating operations of all kinds, operations possible only with direct current. Still another example, furnishing DC in steel mills for the driving of variable speed motors, such as the one controlling this giant ladle, or the ones driving steel conveyors with such precise control of speeds that danger of buckling and tearing and consequent mill damage is eliminated. Electronic rectification is also helping to build American air power by making available record-breaking quantities of aluminum for plane construction. From Arkansas mud to American air power involves a complicated conversion of material. Before pure aluminum can be extracted from this bauxite ore, direct current must be applied in a vital reduction process. To obtain that direct current from AC transmission lines, the Ignitron rectifier is used. This Westinghouse electronic development changes vast quantities of AC to DC with higher efficiency than any similar type of conversion equipment. Today, it's the main source of current supply for the nation's great aluminum industry, an industry that has achieved a miraculous expansion to meet the demands of a world at war. Magnesium from seawater is another achievement of industry under the stress of war. Ignitrons used in the extraction process speed up the delivering of incendiary and demolition bombs to the centers of Axis production. Still another example of electronic rectification at work is the precipitron, a device for cleaning air electrostatically. This diagram explains how the precipitron works. The rectifying property of electronic tubes is used to apply a potential of 13,000 volts DC to tungsten wires and 6,500 volts DC to collector plates. As incoming air passes through the field of these wires, each particle of dirt receives a positive electrostatic charge. When the positively charged particle reaches the collector chamber, it's attracted to and deposited on negative plates. In this way, air is cleaned so thoroughly that dirt particles down to a 1/4 of an inch are removed. This is a vital advantage today, not only in homes and public buildings, but in industrial plants of all kinds. For instance, in plants manufacturing delicate instruments, where air cleanliness is necessary for precision work. In workrooms where optical systems are assembled for a host of military purposes. In inspection rooms where minute parts must be closely examined under high magnification. Air cleanliness is vital, too, in film developing rooms like this one. To understand how electronic air cleaning helps here, let's go aloft in a reconnaissance plane. Click. 5,000 feet above the earth, a camera shutter opens and closes. Scores of square miles of enemy territory have been squeezed down into an image on a photographic plate. An image measured in inches instead of miles. On this photograph, a city might be covered by a tip of a finger. A speck of dust could hide a Nazi airdrome. The rectifying tubes of the precipitron help make sure that dust doesn't sabotage military photography. Now, so far in this film, we've discussed only one of the basic things we can do with the electronic tube. We can use it to rectify. The second basic thing we can do with it is amplify. Here's how. Between the cathode and the anode of the two-element tube, which we diagrammed a while ago, we now place a grid. To this grid, we connect an input of some weak voltage which we wish to amplify, perhaps that of a faint radio signal from halfway around the world. Now let's see what happens. Every time a negative potential is impressed on the grid, even though it be very minute, it has a large effect in reducing the number of the negatively charged electrons which would otherwise keep flying from cathode to anode. Conversely, when the grid is positive, an equally large effect is exerted in increasing the flow of electrons from cathode to anode. The important thing to note here is this. A small amount of power applied at the grid is amplified into a large amount of power in the anode or work circuit. This amplifying property of the three-element electronic tube is put to work in innumerable ways. Westinghouse electronic amplification now helps provide radio and radio telephone contact between airplanes and control stations on the ground, between ships and their communication bases, both afloat and ashore, between individual tanks and their tank force commanders, between firing line and headquarters, between Seadrome lights and night-flying pilots who can turn them on by radio signal. In the field of power engineering, electronic amplification permits the measurement and analysis of minute voltages, stepping them up to the point where they can be seen and interpreted on oscilloscopes. When this giant rotor is completed, its precise dielectric balancing will be made possible by amplifying tubes. Testing of these propellers for vibration fatigue will also be facilitated by electronic amplifying tubes. Up to now, we've considered two of the basic things that the electronic tube can do. It can rectify, it can amplify. A third thing it can do is generate. The term generate in this connection is meant in a general rather than a technical sense. A triode is connected for oscillation in the way shown here. The system then becomes capable of changing direct current into alternating current. Note that what we're doing in this case is amplifying in the usual way and then feeding back to the grid part of the amplified voltage. Continued repetition of this feedback results cumulatively in a strong alternating current. This electronic means of generating alternating current is important because it can produce very high frequencies up to millions of cycles, far beyond the range of ordinary rotating equipment. A familiar application of this is the radio transmitter. This modern transmitting room of Westinghouse station KDKA is a far cry from the pioneering equipment of its famous predecessor. This scene reproduces an historic occasion, the first time a radio transmitter was used for large-scale public entertainment.
This is station KDKA of the Westinghouse Electric and Manufacturing Company. We are about to begin the reading of the presidential election returns between Warren G. Harding and James M. Cox. Stand by, please.
Here is a new, less familiar application of electronic high-frequency generation. High-frequency heating of 200,000 cycles per second is now used to flow tin as the final step in the electrolytic plating of steel strip. After steel strip comes from its electrolytic tin plating bath, it first passes through a washer, then between hot air drying jets. At this point, the steel strip has a coating of tin that is relatively dull and porous. Next comes a vital step. The strip is raised to the top of the heater unit housing, inside of which is a series of high-frequency coils. As the strip comes down through these coils, induced electric current causes heat, which flows the tin almost instantaneously, greatly improving its structure as a protective covering. Here's the result. Tin plate that is mirror smooth, free from porosity, so perfect a protective covering that 1 pound of tin can now do the work of 3. Note the horizontal bars in this close-up. These are parts of one of the high-frequency coils that affect the tin flow. If you look closely, you can see the difference in texture between the porous tin entering the top of the coil and the shiny flowed tin leaving at its base. And these are the tubes that generate the high-frequency current which makes the entire process possible. Another important result of this new Westinghouse electronic process is time saving. Tin can now be flowed at a rate of more than 1,000 feet a minute. Here's another example of where electronic high-frequency generation is doing a job today. Dielectric bonding of plastic and plywood sections in a matter of minutes instead of days. As a result of this application, plywood-constructed PT boats can be produced more speedily. Dielectric heating also cures intricate plastic forms faster and better. Here, a dielectrically cured plastic piece is being given a stress analysis. Carrier current relaying also applies the electronic principle of high-frequency generation. Here's part of the equipment that does the work. This equipment makes possible an enormous increase in the speed with which transmission lines can be cleared of faults. Its effect is to increase the load-carrying ability of a system up to 50% or more. We've now illustrated 3 of the basic ways that the electronic tube can be put to work. It rectifies, it amplifies, it generates. And here's a 4th thing it does. It controls. This diagram illustrates one of the principal mechanisms of electronic control. We use the grid here not to amplify a weak signal, but to control the flow of power to a machine. To do this, we connect the control circuit in such a way that it becomes a function of temperature, speed, time, or any other variable. As a result, grid potential is varied, and the work circuit is automatically closed, modified, or opened. And we can do all this with split-second timing and incomparable precision. Take, for instance, this electronically controlled spot welder. Without sound, without friction, without flame, electronic control on this equipment makes and breaks contact with split-second timing. Seam welding, too, is electronically controlled. As a result, plane parts today are being literally sewn together with electric current as threads. But welding, of course, represents only one opportunity for electronic control. Automatic stepless regulation of motor speeds is another application. Without the smooth acceleration which such control makes possible, delicate materials, such as the capacitor windings being handled here, might be broken under the shock of starting and abrupt speed changes. Now for still another basic thing that the electronic tube can do. It can also serve as a bridge to transform light into electric current. Here's how. We replace the ordinary heat-activated cathode of a two-element electronic tube with one made of photosensitive material. Light can now replace heat as the stimulator of electronic emission. The stronger the light, the greater the electronic emission, and consequently, with the aid of an amplifier, the more power flowing through the work circuit. This is important because it means that photoelectric tubes can function as light relays and so be given an almost infinite variety of jobs to do. Scanning the soundtrack of the talking motion picture film you're listening to right now is one of them. Another is the television camera. The iconoscope used in this camera is merely a special form of electronic tube. Product and process control is still another application. In this plant, a phototroller automatically stops a conveyor belt every time a lightning arrestor comes to its point of inspection. Here, a Westinghouse electronic eye inside the metal housing spots pinholes in metal strip as it comes from the rolls, automatically operating a relay that rejects defective sections, dropping them out of the production line without a moment's loss of working time. One of the most important basic things that the electronic tube can do remains yet to be listed. Besides transforming light into electric current, it can also transform electric current into light. The cathode ray tube is an application of this property. Through the aid of this tube, an electron beam is able to recreate an original image on the screen of a television receiving set. The electronic X-ray tube indirectly also transforms electric current into light, and by its effect on photographic plate, into light images. Here's how an X-ray tube works. A high potential ranging up to 300,000 volts or more is applied between the anode and cathode. Electrons are emitted by a focusing cathode. Due to the extremely high voltage, the electrons hit the anode with tremendous impact and cause the emission of waves of exceptionally high frequency. These high-frequency waves do three useful things: penetrate, excite fluorescence, or affect photographic plates. As a result, doctors can now study human internal organs by means of the fluoroscope. Or by means of radiography, they can photograph them. Industrial X-ray today is also playing a vital role, detecting porosities and fissures in welded metal seams, examining heavy castings for invisible internal weaknesses. But X-ray isn't the only example of electronic usefulness in the conversion of current into light. The whole field of modern fluorescent lighting represents another application. So does the field of ultraviolet radiation. Harmless-looking tubes like this one have a deadly effect on bacteria and other forms of microscopic life. In this demonstration, Parmesia rather than bacteria are about to be subjected to Stereolamp rays. Notice what happens. The Stereolamp today is becoming increasingly important, both as a servant of public health and as a device for the preservation of perishable goods. So many and so varied are the applications of electronics that a single film like this can mention only 1 in 1,000. We haven't even mentioned, for instance, radar, the electronic development that helped save Britain during the decisive weeks of the German aerial blitz. Here's what happened. Ultra-high frequency waves were broadcast into the skies from English defense stations. When enemy planes approached in the darkness or in the fog, these waves would reflect back to the transmitting point, thus giving warning to the defenders of Britain, permitting anti-aircraft batteries to swing into action and RAF planes to rise for combat. Whenever Hitler's bombers attacked, at whatever altitude, from whatever direction, British interceptors were waiting for them. As a result, the Luftwaffe was blasted from the English skies and the tide of war turned. the electronic tube, in essence, is only a switch. But what a switch! It rectifies, amplifies, generates, controls, transforms light into electricity and back into light again. These tubes that look so mysterious are essentially simple in operation, incredibly rugged and sure in application. They open and close all forms of electronic circuits as swiftly as the lightning flash and as silently as the passage of time. In the world of today, they're helping us to win a war. In the world of tomorrow, they bid fair to lift all of us to new levels of achievement, comfort, and security.
This picture is about the transistor. There are 3 transistors here in this collection of small electronic parts. The original point contact type, the junction type, and the phototransistor. And here is a more complex type of transistor. This is called the junction tetrode. These tiny transistors are destined to play a big part in our electronic age. They will make possible smaller, more compact electronic devices that will need less maintenance and have a longer life. But to grasp fully the importance of these new members of the electronic family, let's recall the wonders made possible by the high vacuum tube, the common radio tube. The roots of the electronic age reach back into the early years of our century. In 1907, Dr. Lee DeForest discovered that a grid of fine wire placed between a filament and a metal plate in a vacuum tube could control the flow of electrons between the filament and plate, and the tube could be made to amplify as well as detect electrical waves. He called this amplifying tube an Audion. Weak signals applied to the input or grid of the Audion caused similar and much stronger signals to flow from the plate or output. A few years later, 2 scientists, Dr. Arnold of Bell Telephone Laboratories and Dr. Langmuir of General Electric, working independently, found that by pumping out the Audion tube to create a very high vacuum, they obtained greater fidelity and stability. Here is one of the first high vacuum tubes that started us on the way to the wonders of our electronic age. By 1915, telephone research physicists and engineers had succeeded in developing methods of manufacturing the vacuum tube with sufficiently uniform characteristics so that hundreds of them were installed as amplifiers, thus making possible the first telephone line between New York and San Francisco. And 3,000-mile transcontinental telephone calls became a reality. This same year, 1915, at Arlington, Virginia, telephone engineers hooked together 500 vacuum tubes to generate enough radio power to send the human voice across the Atlantic for the first time in history. Words spoken into a radio telephone transmitter at Arlington were heard by engineers listening at the Eiffel Tower in Paris and also at Pearl Harbor, Hawaii. 1920 brought the beginning of radio broadcasting, but a vacuum tube radio receiver was a real luxury. Then, the next 10 years gave us talking motion pictures, transoceanic radio telephone service, television demonstrations, and ship-to-shore telephony. With our electronic age in full swing, the coaxial cable, the cathode ray tube, the iconoscope, and the image orthicon, aided by hundreds of more conventional vacuum tubes, gave us television, radar for war, radar for peace, and then microwave radio relay to speed hundreds of telephone calls as well as television programs from coast to coast. The heart of all these electronic systems has been the vacuum tube. But the Bell Telephone Laboratories have added an entirely new and different heart to modern communication systems, the transistor, operating on a new and different principle arising from basic research on solid substances and how the electrons inside them behave. How did it all come about? Well, doctors Shockley, Bardeen, and Bratton and their associates at the Bell Telephone Laboratories were working on a problem in pure research, investigating the surface properties of germanium, a substance known to be a semiconductor of electricity. Their study suggested a way to amplify an electric current within a solid, without a vacuum or a heating element. And after months of calculations, experiments, tests, the transistor was born. The transistor, a new name, a new device that can do many of the jobs done by the vacuum tube and many the tube can't do. Let's see how the transistor and tube measure up. First off, the vacuum tube is power hungry. While a tube like this generally demands a watt or more of electricity, a millionth of a watt is enough for the transistor. Even a makeshift battery of moist blotting paper wrapped around a coin can power a transistor. The vacuum tube gets pretty hot, sometimes a little too hot. That's why in complex devices, the tubes must be spaced far enough apart for proper ventilation. Since transistors remain cool, they can be crowded together in a small space. In size, reliability, and ruggedness too, the tiny transistor has many advantages. And research goes on to make it still more useful. Many new and improved types of transistors have followed the early models, but transistors are no longer just an experiment. Here, they are being produced at the Allentown, Pennsylvania plant of Western Electric, the manufacturing and supply unit of the Bell system. Different types for different purposes. The Bell telephone people have lots of jobs lined up for them, jobs based on the transistor's ability to amplify speech sounds in this way. This is how my voice would sound over a 75-mile telephone line that has no amplifying device. Now, with a transistor amplifier in the line, my voice is amplified so that you can hear me distinctly. This, for example, will mean that in isolated farmhouses, far from central exchanges, the transistor, right in the telephone, will make it easier for the farmer to hear and be heard on his rural telephone. And transistors can replace many of the vacuum tubes used in providing long-distance telephone service. Because they are so tiny, transistors have made it possible to miniaturize many types of electronic equipment. This equipment requires less space and will cost less to maintain. Transistors may also be used in multi-channel telephony, which increases the number of calls that can be carried at the same time along telephone lines. When you dial direct from your town to a distant city, transistors in this route selector may be helping to mark out the pathway along which your call will go. Transistors may someday go under the sea, built right into underwater telephone cables. But transistors go well with lots of other industries too. Many manufacturers have been licensed to produce transistors and devise new applications. Through their efforts, you may be able to get music with a flick of your wrist from the so-called Dick Tracy radio. And with a portable television set, you may be able to enjoy video entertainment anywhere you go. For the military, the transistor opens up fantastic possibilities, most of them in too early a stage of development to be talked about. Transistors will take their place in the complex calculating machines that have often been called electronic brains, because they enable man to save days, months, even years in solving mathematical problems. Of course, we cannot build a calculating machine as flexible as the human brain. But even a man-made computer designed to do hundreds of brain-like calculating jobs might need an Empire State Building to house it and a Niagara Falls to power and cool it if vacuum tubes were used in its construction. Substituting transistors for tubes, such a versatile machine could fit into a good-sized room, and power and cooling needs would be relatively low. With the transistor, man has gone far toward matching some of the capacity of the human brain. He has done it with imagination, with the inventiveness and teamwork of the Bell telephone scientists who are looking forward to the age just beyond the age of electronics.
This is a report on integrated circuits with Dr. Jim Angel, Professor of Electrical Engineering and Director of the Solid State Electronics Laboratory at Stanford University, and Dr. Harry Sello, Manager of the Materials and Processes Department at Fairchild Semiconductor Research Laboratories.
Hello. We're here to tell you about a recent revolution in electronics. Of course, there have been many recent revolutions in electronics. You hear about them all the time. We'll tell you what is an integrated circuit, how to design it. We'll go through the agonies of how it's made, and finally, tell you about some of the uses of it and what they're good for. But first, let's have a commercial.
It started here. Pure PN junctions from a pile of sand. Planar silicon integrated circuits. Invented here. The epitaxial process, a secret locked in a crystal. Higher yields in 1/10 the time. Invented here. Metal over oxide. You can't make an integrated circuit without it. Invented here. Fairchild brought out the first NPN silicon mesa double diffuse transistor, the first PNP silicon mesa double diffuse transistor, the first planar NPN transistor, the first planar PNP transistor, the first lifetime controlled silicon planar transistor, the first planar epitaxial PNP transistor, the first silicon RF transistor, the first planar 2 transistor, the first planar silicon controlled rectifier, the first planar epitaxial power transistor, the first resistor transistor logic family, the first complementary transistor logic family, the first dual inline package, the first commercially available face-down bonded circuit. Processes, product, packages, price. Oh yes, and production. Invented here.
Let's get started, Jim, by you saying what is an integrated circuit.
Here is a packaged integrated circuit. Inside this package is a chip of silicon which provides the electrical equivalent of many transistors, resistors, and diodes, all interconnected to provide the desired function. Before we discuss in detail what's inside that package, I'd like to show you some evolutionary examples of what integrated circuits can do for the appearance of electronic equipment. Here is a photograph of a printed circuit board from a digital computer a la 1960.
Prehistoric.
Right, built out of transistors, separate resistors, and diodes, wired together on the printed circuit board. Here is the electrical equivalent of the circuit you saw in the previous photograph, built in integrated circuit form of vintage 1963. Notice how much smaller and simpler this board is. I have here a newer version of integrated circuits containing in the upper left-hand corner 8 integrated circuits outlined. Now those 8 integrated circuits provide essentially the same function that was provided by this board, namely 24 integrated circuits down to 8. Notice that the wiring on this package is extremely orderly and well organized.
I see less pin connections, too.
This is perhaps typical, Harry, that we find as we make a more complex function in one structure, the number of pins tends to go up only as roughly the square root of the complexity that's provided by that board. Now you've seen an evolution of transistors to early integrated circuits to modern ones. Let me show you a series of photographs which shows you what's inside the corresponding cans. Here is a photograph of a single transistor chip, such as we might find in the 1960 version of the computer board I showed you.
Old style again.
Here's the intermediate style. You remember the 1963 integrated circuit packages. Here's what would be in one of them, typically 10 transistors. Here is a modern 1966 version of integrated circuits with many hundreds of components on this one circuit. This particular function provides 16 bits of digital memory in this one package. Now, integrated circuits can not only be used for digital, but also for linear service. Here is an IF strip, transistorized and hence perhaps 3 years old. Here is its integrated circuit counterpart, providing exactly the same function. Notice how much simpler it is. The wiring is roughly the same. the simplicity is greater. Hence, we can expect that it will not only be cheaper, but more reliable. And these are perhaps the most important contributions of integrated circuits.
Let's get on to how to design an integrated circuit.
All right? Let's do it by way of an example. Up here we have a circuit for a typical structure which might be in integrated form. This particular circuit has 20 components in it: diodes, transistors, and resistors. After the configuration has been chosen by usual techniques, the next step is to build a breadboard model in actual working form. On the breadboard, we have separate transistors and other components, all actually wired into a working circuit. The purpose of working with the breadboard is to try to optimize the numerical value of each of the components in the circuit. Once this optimization has been achieved, the next job is the design of the masks, which will be used to make the integrated circuit. Harry, I wonder if you could cover some of that work.
Yes, I can. So, we made the engineer pick up a soldering iron. Let's see if we can make an artist out of him by using yet another example. Here is a full-scale 30 by 30 inch piece of typical integrated circuit artwork, which represents in a careful, precise form the interconnection pattern of an integrated circuit. For example, these are the metal pads. These will be on the integrated circuit, the metal pads, which connect to the outside world. Here we have the transistors. And here are diodes and more interconnecting metals. The problem here is to very carefully and precisely convert this large-scale drawing into a small, precise version of this on a 2 by 2 inch glass plate. This artwork is reduced 500 times by a process of high-resolution photography to a glass plate upon which the pattern shown by the artwork is successively stepped and exposed all the way across the glass up to 1,500 times, which means, of course, 1,500 integrated circuits. Now, the artwork which I showed was only one mask, potentially. Here is the artwork in reduced plastic overlay version, which goes with a complete set to make an integrated circuit. There are 5 to 7 or even more of these potential masks. All of these must align carefully and precisely. These then will be translated into another set of glass masks, which will then be used for contact printing directly onto silicon wafers. In working with silicon, this is what you begin with: a silicon ingot. It's a glass-like material, very brittle, very much like diamond. In fact, it costs about like diamond and is a member of the diamond family. This is made in a series of long rods by a process known as crystal pulling. It cools as it is pulled. However, it is still very hot since it's been grown at a very high temperature, up around the region of 1,400 degrees centigrade. We cut this into thin wafers, about 12 thousandths of an inch thick, by using a diamond saw. After cutting, the wafers are very carefully polished, so you end up with a mirror-like surface, which is essential in the preparation of the integrated circuits. The finished chip is about 5 thousandths of an inch thick. Let's take a look inside the silicon. This is a cross-section of the wafer we've just watched being made. To protect it from the outside world, we allow oxygen to react with the top surface and grow an oxide called the passivating silicon dioxide layer. Now we're going to make use of the masks we made earlier. First, the wafer is coated with a photosensitive resin. The mask is then placed on the wafer, and the system is then exposed to light. As a result, the exposed resin hardens. The remaining resin can be simply rinsed away. The wafer is then exposed to acid. Those areas of the passivating layer not protected by the hardened resin are etched away. In the next operation, called diffusion, the wafer is exposed to a dopant. This impurity diffuses through the window and into the silicon below, forming the collector of a transistor in our integrated circuit. But notice, At the same time diffusion is taking place, more oxide is being formed. This is the essence of the planar process. Now we're going to strip off the passivating layer and grow a new layer of silicon right on top of the diffused wafer by a process called epitaxial growth. Now we form electrically isolated regions on the wafer by a process of diffusion, photosensitive coating, masking, exposure, rinsing, etching, and diffusion. Next, we prepare the individual parts of the integrated circuit. First, a transistor base and a resistor. The same procedure is followed. Notice that diffusion takes place not only downwards, but also laterally under the oxide. As a result, the junction is formed beneath the passivating layer, where it is protected from the outside world. The next diffusion forms an emitter and a collector contact to complete the transistor. Again, the same process. The next step enables us to interconnect the various components and to make contact with them. Again, we'll etch windows in the oxide. But instead of another diffusion, a layer of metal is deposited over the entire surface of the wafer. Then, by use of the proper masks, the excess metal can be etched away. Sometimes we like to make resistors a different way, by using the metal interconnection pattern. All you have to do is make the metal pathway a little narrower, and it provides higher resistance. If we wish to make a capacitor, we take advantage of the fact that the oxide layer is an excellent dielectric material. A small area of metal is deposited, forming one plate of a capacitor. The oxide is the dielectric, and the silicon directly below the oxide forms the other plate. The series of schematic operations taking place on one structure that you just saw actually takes place across a whole wafer. This results in a wafer containing many integrated circuits, up to 1,500 of them. Now comes the electrical testing of this wafer. Jim, can you take over on this part?
Certainly, Harry. Even though we have been very careful in fabricating this wafer containing many hundreds of integrated circuits, not all the circuits on the wafer are flawless. The first job is to determine and mark those circuits which are not good. We test the wafer in a probe testing machine. We then scribe the wafer using a diamond point in the scribing machine. After separating, cleaning, and drying the integrated circuits, we fish out the ones that are bad. If we have been successful to this point, we have a high yield of good ones. From this point on, we're going to package the circuits, and so whenever we throw one away, we're going to throw away a complete package.
That's a good point, Jim. Let's look into this matter of packaging a little bit. You know, we've exercised a lot of care in bringing the integrated circuit chip to this point in the processing, and we've also done it economically, because mostly we've processed them as wafers, 1,500 at a time. From here on out, as you pointed out, we will be handling them as individuals, putting expensive packages around them. So how we treat the packages is important. In the old days, it was simple. You had a wide choice, two, large and small. A TO18 outline, small, and the TO5, larger outline. These days, we have upwards of 250 varieties of packages, and a user can select any one of them. Here are an example of three of these. A dual inline package, a plastic package, and a flat pack. The most nearly universal of these is the dual inline package. Let's take a closer look at just how that is made. You start out with the idea that you're going to build a tasty but inedible sandwich. Here are the two halves that you begin with. Two ceramic parts into which the integrated circuit chip will form the sandwich meat. The two halves are glassed with a material which will form the solder that glues the two halves together later. A Kovar frame has been prepared in advance and cut out to the pattern necessary to connect the chip to the outside world. This Kovar frame will also be placed in the middle of the sandwich alongside of the chip. And here is the arrangement. Chip in center, Kovar frame around the outside, and notice that the tips of the frame here have been metallized. This will form the connection to the chip directly, as shown here, where the lead bond wires have been placed connecting the pads on the chip to the metallized tips of the Kovar frame. We complete the sandwich by putting the top half of the package right on top of the frame. The next operation will be to clip the ends of the frame. The package is now revealed in its magnificent beauty. The solder glass is peeping out, so that we have to clean that up a little bit by sending the part through the furnace along with many thousands of others, so that the solder glass is all melted in and neatly arranged in place. This is the finished dual inline package.
Now that the circuit has been packaged, we must again test it substantially before we would dare ship it to the user. First is a series of electrical tests, many of which use special test equipment, which is again built from integrated circuits. Many of the tests made on the integrated circuits now duplicate those tests which were made on the wafers. In addition to these tests which duplicate those which were made before, we must make some special tests, such as frequency response of a linear amplifier or switching speed of a digital circuit, before we would dare ship the unit. We can't make these tests on the wafer state due to the limitations of the test equipment through the probes. In addition to these electrical tests, we make a variety of mechanical tests, such as shock, vibration, and acceleration. Finally, we make a set of temperature tests, running the unit at high temperature and at low temperature to ensure that the unit will work dependably in service.
Now let's look into some of the things that we can do with integrated circuits. But first, a commercial.
For the past year or so, Fairchild has been publishing a series of applications notes on integrated circuits. If you read the design journals, you might have seen one, if the guy ahead of you didn't tear it out. They talk about the switch to integrated circuits, how to design them in, when to use them, which ones, their costs, basic design rules, a pretty complete short course. Then, on the back of each sheet, we've covered a specific industrial application, an XY controller, a tape reader and display, a cycloconverter. A dozen ideas. But if you're really serious, you'll have to read the book. It covers all the IC families. Digital, linear, hybrid, memory, custom. It tells about packaging, testing, and of course, how to order ICs. Altogether, that's about 100 pages of fresh information on integrated circuits. We'll send it to you if you'll write us. Got a pencil? Fairchild TV Briefing, Box 1058, Mountain View, California. We'll send you the whole stack by return mail.
Now that we've talked about how to design, build, and test integrated circuits, let's look at some of the functions which are available now in integrated circuit form. Here's a list of readily available digital circuit functions. This list includes about all the circuits which are needed to build the electronics part of a digital computer. This list of linear functions includes a large variety of things. As you probably know, operational amplifiers, for example, are rather precise amplifiers that are used as the major building block of analog computers. The voltage comparator is a circuit which very accurately compares which of two voltages is the larger.
You know, it's exciting to think that all of these functions are here today. They can be used. They're available. And it's even more exciting when you consider the number of applications that these can be put to. You couldn't even begin to make a list of all of them. Actually, the uses of integrated circuits are limited only by those who are designing these uses. Let's take a deeper look into some of the present-day applications of integrated circuits. One of the many industrial companies using integrated circuits today is Burroughs Corporation. At Burroughs, integrated circuits in dual inline packages are inserted in circuit boards automatically, affording more efficient production. Using this machine, which is proprietary with Burroughs, a single integrated circuit can be installed for about the same cost it previously took to install a discrete component. In order to automate the entire manufacturing process, Burroughs uses other advanced techniques such as flow soldering. This guarantees reliable connections to each integrated circuit. In addition, computerized wire wrapping machines are used to make the backplane interconnections so that the inherent reliability of the integrated design isn't compromised. The machine automatically cuts each wire to the correct length, strips the ends, routes the wires, and makes the connections. Meanwhile, each completed circuit board is tested individually. Finally, circuit boards are installed in the computer frame, and the completed system is thoroughly tested. Burroughs is now committed to integrated circuits, and in fact, recently placed one of the largest single orders ever placed for these devices. For Burroughs, integrated circuits provide a significant cost reduction and a proven increase in reliability, both of which are real benefits to Burroughs customers. Stromberg Carlson is another company committed to integrated circuits. Their Data Products division is now manufacturing the first in a line of new Stromberg Carlson products built with ICs. Integrated circuits, in this case in TO5 packages, both metal and plastic, were used in the SC1100 because of their low cost, size, reliability, and, as Stromberg Carlson says, because integrated circuits are here to stay. The SC1100 system consists of up to 18 desktop interrogators like this one, which are handled by a single station control unit, which in turn ties into the computer memory. The operator asks the computer a coded question on the interrogator. The computer responds with the requested information almost instantly. For instance, with an employee personnel record. This is the Model 388 AM/FM stereo receiver built by H.H. Scott. It's only one of a new line of hi-fi components in which linear integrated circuits replace discrete transistors. Scott engineers have chosen ICs for one specific purpose: better performance. More stations can be pulled in with less noise and interference. Weak stations become loud and clear, and outside interference is drastically reduced. But there are other benefits too. A total of 37 discrete components in the receiver's IF strip have been replaced by only 4 ICs. This new approach to circuit design promises even more dramatic new products from the people at H.H. Scott. We've seen some examples of how industry is putting integrated circuits to work today. But how about the future?
Well, that's a very exciting part of the story. Research has constantly gone on to find new ways to use integrated circuits. Not only in the R&D labs of semiconductor manufacturers, but in the universities, like here at the Solid State Electronics Laboratory of Stanford University in Palo Alto. The facilities you see here in this integrated circuits lab are made available by funds from many industrial organizations. Our lab at Stanford is a miniature of the production facilities you've seen in industry. It was built with the help of contributions from the majority of our nation's semiconductor manufacturers. Right now, we're working in several areas. We do basic research in integrated circuit technology. We're doing circuit research using the unique capabilities of integrated circuits.
We also develop devices which incorporate ICs. And we conduct research in several peripheral areas. As an example of our research in IC technology, we're studying new ways for getting impurities into semiconductors. Normally, this is done by diffusion. We do the same thing by ion implantation. This machine takes individual ions and accelerates them, ramming them into semiconductor material much the same as you would shoot a bullet into a bale of hay. Right now, this is a much more expensive process than diffusion, but it's a different technique. Here we're not interested so much in developing the technique as we are in learning the fundamentals. How heavily can you dope materials, and what kinds of materials can you dope this way? Let's look at an example in the field of medical electronics. Here we're using IC technology to develop an array of fine probes which a neurologist can implant down in a living brain to study the potential at different points on a single neuron. Here, you're looking at one of the masks prepared by the student doing this research. We're developing probes using the same technology as for the metallization patterns on ICs. The probes will probably be of gold. This would have been impossible before IC technology. One of the most dramatic devices being developed is this reading aid for the blind. This is a reading device in which ordinary printed material is converted to a tactile image which is presented by a closely spaced array of 48 piezoelectric reeds. By resting his finger on the vibrating reeds, the blind person can sense a vibrating and grainy facsimile of the material being viewed. The great advantage is that this machine enables a blind person to read the printed page. This version is relatively large, even though it incorporates integrated circuits. Ultimately, one 70 by 90 mil chip will take care of all the necessary electronics to drive one vibrating reed.
Certainly, integrated circuits are used in many present-day applications, but we mustn't forget one very important factor, and that is the reliability of an integrated circuit. It is a reliable device. In the industry, we've logged almost 80 million element hours without a failure. That's reliability.
We have considered many different things regarding integrated circuits. One question which we might ask is, why do people care about integrated circuits? Well, there are many reasons. Certainly one of them is the reliability factor that we were just considering. The second one is the fact that they are inexpensive. Even today, it is often less expensive to do a function with integrated circuits than it is with separate discrete components. The fact that they are small is important. This board here contains many functions, many more functions than we could get in this volume otherwise. Finally, there are new functions which can be achieved with integrated circuits that just plain couldn't be achieved any other way. Harry, we've considered a large variety of topics on this program. I'm wondering if you'd be willing to summarize it for us.
Yes, let's summarize. We started out by telling you what an integrated circuit is. This is an integrated circuit. It's a piece of silicon into which have been built all of the necessary components to perform an electronic function. The piece of silicon in a blow-up picture looks like this. All of the functions are there. We've taken you through the design and building of an integrated circuit, from a circuit diagram through masking to wafer processing, and finally on to the final packaging of an integrated circuit. We've showed you that it takes a lot of extensive testing to prove out an integrated circuit. And finally, you've seen a lot of the uses, both present day and future uses, for integrated circuits. Hopefully, we've given you some ideas on how you can put integrated circuits to work for you.